All right, good afternoon, lads and ladies. Welcome back. Today we are going to continue learning about areas. We're also going to look at some neat connections to physics. I want to talk with you a little bit about a few things. Mostly, I want to show you where certain summation formulas come from, and get a little bit of time doing some examples. So let's jump in. This is MAC2311.0H1. It's a lecture, and today is the 19th of March. Today we're going to do more 5.1 stuff. We're going to look more deeply at that sigma notation, and we're going to talk about distances, how you can connect areas under curves to distances traveled by an object or a particle. It's very cool. Last time, though, we didn't get to talk a whole lot about sigma summation notation, so I want to start with that. The notation here is very important, so please take careful notes and get good practice with this notation. I know that not everybody has a sufficiently strong pre-calculus class to have seen the amount of practice with the sigma operator that we really should be able to expect. So unfortunately, it's one of those things that's usually discussed at the end of pre-calc. Pre-calc is a very busy class, and so often it kind of gets bumped or pushed, and that's a tragedy. So let's get to it. Definition's the place to start. With sigma operator, if I have something like sigma I equals 1 to n, what this stands for is a big, long addition problem. The Greek letter sigma here is actually the capital Greek S. It makes the S sound in the Greek alphabet. And we use this because S stands for summation. So sigma is the Greek S, and it stands for the word sum, meaning to add up. So sigma I from 1 to n of some stuff, you need to have some stuff in here, which usually represented by a lowercase letter when we're talking about sums in general of AI. You take this thing as I runs from this number up to whatever this number is, and you add them all up. So this would be A1 plus A2 plus A3 plus A4, A5, A6, whatever, all the way out to AN, whatever n is. And I want to get a little bit of practice just evaluating these sums, writing things as sums. So let's jump right in and do a bit of that because you have some of these problems in your homework. Just so I have a feel, could you give me a thumbs up react here in Zoom if your pre-calculus class did cover this stuff? Okay, so just a couple of us. The majority of us need more experience with this. All right. So we'll start simple. For example, if I give you sigma I from 1 to 4 of 1 over I, how would you expand that out? I see, okay. This would be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. So it's just a more compact way of writing this longish addition problem. And it gets more and more useful the longer and longer the addition problem is. We could evaluate this if we wanted to. My common denominator here would be 12, right? So this would be 12 over 12 plus 6 over 12 plus 4 over 12 plus 3 over 12. And so what would that be? That would be 12 plus 6 is 18, plus 2 is 22, plus 3 is 25. So this would be 25 twelfths. The sum doesn't always have to start at 1. It could be like sigma I from 0 to 5 or whatever of 2 to the I, like this. So if I wanted to write this out, if I had to evaluate this sum, my first step would be to write it out. Writing this out, I'm just going to plug in all these values for I into this expression. I'll do that for I equals 0, I equals 1, all the way up to 5, and I'm going to add all those together. So that would be 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3 plus 2 to the 4 plus 2 to the 5. Looks like I'm going to need some space here. So this is 1 plus 2 plus 4 plus 8 plus 16 plus 32. So what is this? This is 3 plus 4 is 7. 7 plus 8 is 15. 15 plus 16 is 31. 31 plus 32 is 63. So if I had to evaluate these sums, if I was asked to do that, this is how I do it. I first just write the thing out using the definition of the summation operator. So I go from here to here, and then I clean it up. You can go back the other way also. I can write the expression say 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared in sigma notation. And this is an important skill to have also, right? Not just evaluating things that are given to you in sigma notation, but taking something that's not in sigma notation and putting it into sigma notation. Here, what I notice is that everything is being squared. And the things are 1, 2, 3, 4, and 5. So I here would run from 1 to 5. And the thing I'm adding up is I squared. So this would be sigma I from 1 to 5 of I squared. This notation can take a little bit of getting used to, especially if you haven't seen it before, but you're going to want to take the time to get used to it, because in your homework this week, and there is homework this week, you have a handful of problems that ask you to do precisely that. So the first few problems here are just like the ones we were doing in class on Wednesday, where I give you some function, I give you a range of x values, like an interval, and I say estimate the area under the graph using some number of rectangles, right? And left endpoints or right endpoints. So you want to go through it exactly the way we did with the problems we were working last time. But then after you get through those, there are some questions about velocities and distances. We'll talk about that in a little bit. And after those, you have some problems that kind of try to introduce you to this sigma summation notation. So what we're just discussing now is precisely what you need in order to do these. The reason we have you doing those is because after that, you're going to be finding the exact area under the curve, or at least an expression for the exact area under the curve. And this requires taking a limit of Rn. And since that is best written in sigma notation, you need to be comfy with these. So you'll notice that your answers here are meant to be given in sigma notation. They've already provided the capital sigma for you, so you won't need to type that. You just have to type what goes in here. But we'll come back to that in just a second. Anyway. There are some rules for the sigma operator. Which will be useful, not just here, but also in Calc 2. In Calc 2, we do a lot of this sigma notation work. Two main rules. The first one is that if you have a sum, sigma I from 1 to n, with two things inside being added up, maybe like ai plus bi. So this could be like I squared plus I cubed, or 1 over I plus 2 to the I. If you want to evaluate the sum of those things, you have the option of splitting it up. You could write that as the sum from I equals 1 to n of ai plus the sum from I equals 1 to n of bi. And as is usually the case with this sort of thing, if this were a minus in here, this would be a minus out here. Similarly, if you have a sum from I equals 1 to n, and inside you have a constant times your function of I, c times I squared, or c times 1 over I, that constant can pop out. And these two rules should look familiar. You can split up over addition and subtraction, and constant multiples pop out. Those are the same two rules that we have for the derivative operator. These two things together are called linearity. The capital sigma operator is what's called a linear operator. And we love linear operators in mathematics. They are just the knees of the bee. In order to pop something out like this, it's important that the c is a constant. But it needs to be a constant with respect to the sum. What that means is that it has no i's in it. So sometimes we will pop things out of sums that look like variables. That's okay, as long as it's not a variable when considered with respect to the sum. And what makes it constant with respect to the sum is that it doesn't have any of these indices I in it. So I'll show you precisely what I mean in a second. But first, since this is an honors class, I want to run through the proofs here. The proofs here are not difficult. But they can provide some insight into this operator. So here's the proof. For one, I'm just going to write this out. I'll prove it in the case where you've got a plus there. So sigma I from 1 to n of ai plus bi. This is by definition a1 plus b1 plus a2 plus b2 plus all the way out to an plus bn. But you know that addition is associative, so these parentheses can go away. This is a1 plus b1 plus a2 plus b2 plus the next term would have been a3 plus b3, and we're going to go all the way out to an plus bn. And then you also know that addition is commutative, meaning you can kind of move the order around. So I can take this a2 and put it over here. So I get a1 plus a2. I can take the a3 that's in here and shuffle it over there. I can take all the a's and put them together. And that will be added to what I have with all the b's put together, b1 plus b2 all the way out to bn. And now if I rewrite this in sigma notation, this first piece is sigma I from 1 to n of ai, plus the second piece is sigma I from 1 to n of bi. And that's the proof. Sigma ai plus bi is equal to sigma ai plus sigma bi. And if these were being subtracted, the same sort of shit would work just fine. The proof of the second item is also not difficult. Sigma I from 1 to n of c times ai is by definition c times a1 plus c times a2 plus on and on and on until we get to c times an. And what you notice is that every term in the sum has a c in it, so you can factor out the c. And what's left would just be a1 plus a2 plus on and on till you get to an. And what you see inside the bracket there is, by definition, sigma I from 1 to n of ai. So like I said, these proofs are very, very simple. But they help us see what's going on with the summation operator. And the other things I want to share with you regarding capital sigma before we dive back into problem solving is a few summation formulae. One of these has a really good story behind it. So the first formula here I'd like to give you is one that you could guess. If I sum from I equals 1 to n, the object 1. Let's think about what this is. This says I'm going to add this to itself as I runs from 1 to n. So when I is equal to 1, this thing would be 1. So we're going to add that to what we get when I is equal to 2. Well, when I is equal to 2, 1 is just 1. This is a constant. Plus, when I is equal to 3, 1 is still just 1. Plus, all the way out until we get to the last term, which would be 1 as well. This is just 1 added to itself n times. And 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 n times, that's always going to come out to n. The next formula I want to give you is the one that has the good story behind it. So one of you is doing your project on Carl Friedrich Gauss, right? The German mathematician Gauss. It's said that when Gauss was a young boy, somewhere around 7 or 8 years old, second grade-ish, he was incredibly precocious, right? Like little kids, when they're excited and knowledgeable, they like to shout out answers and they're very proud of themselves. Gauss was like that. Now, that's not too hard to imagine, given the man was a fucking genius. So he was constantly disrupting his class, making corrections to things his teacher would say, shouting out answers before anybody else had a chance to talk, that sort of thing. So one day, in order to get baby Gauss to shut up for a minute, Gauss's teacher said, "Baby Gauss, go off to the side and just add up all the numbers from 1 to 100. And baby Gauss came back very quickly with the answer. And the teacher was like, what the hell did you do? And Gauss said, well, easy. I just proved this formula that I'm about to show you and then plugged in 100 for n. So here's the recipe. Of course, what this sum represents, this is 1 plus 2 plus 3 all the way out to n. It's the sum from I equals 1 to n of just I itself, plus the sum of the first n integers. It's equal to n times n plus 1 over 2. Here's how this works. If you take the first and last term and add them together, you get n plus 1. If you take the second term and the second to last term, which would be 2 and n minus 1, those also add up to n plus 1. And if you think about this big long sum, as you pair things in from the outsides, you get n over 2 copies of n plus 1. There's a little bit of subtlety to deal with whether n is even or odd. If n is even, this pairing works beautifully. If n is odd, then there's like a leftover term in the middle, but it turns out to always work. It always works. It's very, very nice. So this is the second summation formula that you're going to need to evaluate Riemann sums for exact areas. There's two others. They are the sum of the first n squares and the sum of the first n cubes. This first guy, of course, is just shorthand for 1 squared plus 2 squared plus 3 squared all the way out to n squared. And I think we used this in class on Wednesday. This is n times n plus 1 times 2n plus 1 all over 6. And the sum of the first n cubes, which would be 1 cubed plus 2 cubed plus 3 cubed all the way out to n cubed. This turns out to be the square of the sum of the first n integers. This is n times n plus 1 over 2 all squared. And there are some great ways to understand these. I don't quite have time to go through all the proofs. The first one should be self-evident. The second one, baby Gauss proved for us. You just take the last term and the first term, and then the second to last term, and the second to first term, and the third to last, and the third to first. Add all of those up, they all add up to n plus 1, and there are n over 2 of them. So it's n over 2 times n plus 1, or n times n plus 1 over 2. These other guys require a little bit more work, and they're really good exercises in proof by induction. If you've ever heard of that and you want to get good at it, you can prove these using mathematical induction. But there are also geometric proofs. So let me see if I can find a link here for you. So sum of cubes. The sum of squares proof is a little bit better known. Oh, I don't know Gauss. Of course, Gauss had a proof for this, motherfucker. Right, so here's the proof for the n times n plus 1 over 2 thing. You take 1 and you add that to n, you get n plus 1. Take 2 and you add that to n minus 1, you get n plus 1. Take 3, you add that to n minus 2, you get n plus 1. So altogether you have n over 2 copies of n plus 1. Now, I'm not familiar with the Gaussian proof they're giving here, but there is a well-known geometric proof. That's not it either. Okay, yeah, this is a good proof for the sum of cubes, if you want to see it. It's the last one, but the sum of squares proof, where is that? Yeah, this is the one. This is a good one. So I'm not going to play the video for you here, but if you are curious, I invite you to please watch this. It's quite cool. All right. So I'd like to work a problem where we make use of one of these. Let's go ahead and do it. I think we just did one last time today. I'm going to do one more. And then we're going to talk a little bit about connections to physics, which there are many, but here there's a particular one that's fun. Okay, so what I want to do here is find the exact area under the curve x squared plus 1 from x equals 0 to x equals 1. Now remember last time we saw that the exact area is equal to the limit as n goes to infinity of Rn. So that's what we're aiming to calculate here, where Rn is sigma I from 1 to n f of xi times delta x. And delta x is always b minus a over n, and xi is a plus I times delta x. So what we need to do is figure out delta x. This is one of those, we talked about the two kinds of problems that show up in 5.1. There's the problems where you have a fixed finite number of rectangles, like approximate this area using 4 rectangles, that sort of shit. That's your first 2 problems in WebAssign. The other type of problem that you encounter here is where you're supposed to find the exact area. And there we treat n as a variable because our goal is to take the limit as n goes to infinity. So here, delta x, we've got to identify our a and b. A is 0 and b is 1. Right? A and b are the endpoints of the interval over which I'm trying to find the area. So this is b minus a over n, which is 1 minus 0 over n, which is 1 over n. And the x sub i's, the xi, these are a plus I delta x. And you notice I always write the formula before I plug in. That's a really helpful thing. I recommend you do the same. This is 0 plus I times 1 over n, which is just I over n. So I've got my delta x, I've got my xi's, so I'm ready to set this up. The exact area is the limit as n goes to infinity of Rn, which is the limit as n goes to infinity of sigma I from 1 to n f of xi times delta x. Not doing anything yet, just getting started setting up. Now I'm going to go ahead and begin to plug things into this rather scary looking formula. The things that I just calculated are what I'm going to plug in. Delta x, I know that that's 1 over n. And the xi's, these are my sample points. I know that those are I over n. So this is lim n to infinity, sigma I from 1 to n, f of I over n times 1 over n. Pay very careful attention to the notation, right? Notation matters a lot here. F of I over n, this is not multiplication, of course, right? This is function notation. This is f of I over n. F of x is x squared plus 1. So f of I over n, this piece is going to be I over n squared plus 1. Everything else stays the same. I have lim n to infinity, sigma I from 1 to n, I over n squared plus 1. And I'm putting the whole thing in parentheses because it's all getting multiplied by 1 over n. That's important. Times 1 over n. And this is where we're going to start to use those rules for the sigma operator. First, I'm going to distribute this 1 over n. I'll distribute it over these terms. I'm going to square this out. Then I'm going to split up the sum. Then I'm going to bring out whatever constants I can from both sums. Then I'm going to apply the summation formulas. Then I'm going to take the limit. Sigma I from 1 to n with my limit out front. I over n squared is I squared over n squared. So I have that plus 1 times 1 over n. Now I distribute the 1 over n. So I have lim n to infinity, sigma I from 1 to n. Distributing the 1 over n, I get I squared over n cubed plus 1 over n. And now I can use my rule for the sigma operator that says sigma of one thing plus another thing is sigma of the first thing plus sigma of the second thing. But I've got this limit out front, and I need to make sure that that limit applies to everybody. So this will be limit n to infinity. I'll open up a bracket here. And then inside, I'll have sigma I from 1 to n, I squared over n cubed plus sigma I from 1 to n, 1 over n. And now I know these are quite long, but we need to be brave. We're almost there. I squared over n cubed. So at this stage, I'll make the observation that I squared over n cubed is the same as 1 over n cubed times I squared. And 1 over n, this might seem silly, this is 1 over n times 1. So I'll take the extra step here, why not? Lim n to infinity, bracket, sigma I from 1 to n, 1 over n cubed times I squared, plus sigma I from 1 to n, 1 over n times 1. Why on earth is this useful? Well, remember what I said earlier about pulling constants out of sums? This 1 over n cubed is a constant with respect to the sum. 1 over n cubed doesn't have any i's in it. The I squared isn't a constant. He has to stay inside this sum, but the 1 over n cubed can come out. Similarly, over here, this 1 over n is a constant with respect to the sum. It doesn't have any i's in it. The 1 doesn't have any i's in it either, but I'm going to leave him in. So I can pull this out of this sum, putting him out front here. I can pull this out of this sum, putting him out here. This will give me lim n to infinity, bracket, 1 over n cubed times sigma I from 1 to n of I squared, plus 1 over n times sigma I from 1 to n of 1. And if you apply some kind of lecture logic, you know we have a summation formula that looks like this. And you know we have a summation formula that looks like this. So even if you weren't right away aware that you could pull the n cubed, the 1 over n cubed, or the 1 over n out, knowing that we have a formula for stuff that looks like this hints way back at this line that this is what we want to do. I know that if I just had sigma of I squared, how to handle that. So I'd love to get everything else out of there. I know that if I just had sigma of 1, I know how to handle that. So that tells me to split this up, pull the n cubed out here, pull the n out here. Doing all of that gets me here. Questions so far? This is all the hard work. All the hard work is done. Okay. So we've reached the good spot. This is now lim n to infinity, bracket, 1 over n cubed times the sum of the first n squares, which is n times n plus 1 times 2n plus 1 over 6, plus 1 over n times the sum of 1 from 1 to n, which is just n. This is where I use my summation formulas. Now I clean all this shit up. I take the limit using techniques from 2.6. The first limit is actually one that we've done before. We did it on Wednesday. N times n plus 1 times 2n plus 1 over 6n cubed. Plus over here, n over n is just 1. If we multiply all this out, I'll have n squared plus n times 2n plus 1. So that's going to be 2n cubed and then n squared plus n, so that's n squared times 1 plus n times 2n, that's plus 3n squared. And then n times 1 is going to be n all over 6n cubed. And we have our plus 1 here. And by renormalizing, I can find that this limit is going to be 2 over 6 plus 1. It's the ratio of lead coefficients. You can use that old trick too. So this is 1/3 plus 1, which is 4/3. So the exact area under x squared plus 1, we can look at this. Here's x squared plus 1 from 0 to 1. All right, you know that this vertex is here at 0, 1. This xy over here is 0. The area I'm finding in here is this. This area is exactly 4/3. Cool stuff, right? So we can find the area under curvy shit. That's so big of a deal. Finding the area bounded by a curve, a non-flat curve, is a seriously hard problem that plagued mathematicians for literally thousands of years. The trick is to think of it as infinitely many rectangles. So you find a formula for the area under n rectangles, and then you send n to infinity. It's a tricky, tricky thing, but it's far from impossible. We will develop better ways of doing this soon. There is a wonderful theorem called the fundamental theorem of calculus that connects this idea, specifically the Riemann sum, to something called an antiderivative. And that's what Katie is going to teach us about next week. She's going to teach us all about antiderivatives. And then I'll come back in and draw the connections between antiderivatives and areas for you. So beautiful process. And for now, we really need to work to understand these Riemann sums, because it is what everything is built on, not just all of the area problems we're going to do in this class, but all of the area problems you're going to do in Calc 2 as well. They're all built up from this idea of a Riemann sum. So even though this process may feel incredibly tedious, and I'm on your side there, I get it, this kind of sucks, right? Like this is a lot. Even though this feels tedious, you must get comfy with it. I'm here to help. Come to office hours, send me Canvas messages, talk to each other on the Discord, talk to my other class on the Discord. You guys can talk to my non-honors Calc 1 students there as well. Everybody is working on this right now. So please spend the time to get comfy with Riemann sums. There are a few steps here that I think even somebody who had a good treatment of sums in pre-calculus would struggle with. Namely, I suppose everything from here down to here is a little bit tricky. There's a lot of notation. You need to make sure that you're continuing to write your limit, you're continuing to write your sigma, and that you're very, very careful with the algebra you do in here. But as long as you do that, everything will come out okay. You should always be able to break these down into something like this, where you can then apply summation formulas like these. And then it's just a matter of taking the limit. Are there any questions we'd like to ask about this problem? Any particular step we want to look at more carefully, or anything that I can help you feel more comfortable with?
So how do you come up with the summation formulas? Like, do you derive them or do you just memorize them?
Generally speaking, we just memorize them. What you'll notice is that in the homework problems that ask you to do something like this, they kind of remind you the summation formula. And on a test, if I were to give you a problem like this, I would do that as well. I would say, first set up the Riemann sum, then use this summation formula to find the limit. But it is a wise thing to remember them. So for the purposes of testing, if we're worried about everything fitting in our brain that we need to remember, you don't need to memorize the summation formula. We don't want to cook them up each time we need them because the proofs for most of them are a little bit complicated, and it's a little hard to cook them up. But yeah, most folks will eventually memorize these.
Got it. Thank you.
Of course. What else are we thinking? I'd love to hear your thoughts. I see there's something in the chat. Yeah, the only problems where we have to work with sums are going to be these sort of things. And the only ones where I'll ask you to evaluate directly a sum like this will be either a constant or I squared or I cubed. I wouldn't ask you to go beyond that, although there are formulas in general. They get a little bit tricky. So what you'll find is that I think in your homework, I've only given you one problem where you need to go full hog, finding the expression and then evaluating it using a summation formula. The other questions like this just ask you to find the expression. You don't have to evaluate it. So like, for example, on number 12, they want you to use the definition lim n to infinity Rn to find an expression for the area under the graph. You don't have to evaluate. So here you would not need to use a summation formula here. You just need to get to like this step. But really, I suppose you could stop at even this step on those other ones. So there's only one problem where we have to go all the way. Although it is likely going to be the case that on your exam 3, you will have at least one problem that asks you to go all the way like that. And on that problem, I will give you the relevant formula. But you need to remember the definition of the Rn and the definition of Ln. You need to remember that the exact area is the limit as n goes to infinity of Rn. And you need to be comfortable going through all the steps that get you to here at the very least. And then the remaining steps, I'll only give you one problem where you have to do it on the test probably, but there will be at least one problem on that test where you've got to go through here. So you need to be comfortable with the definition of Rn, with the exact area being the limit as n goes to infinity of Rn. And you need to be comfortable breaking the sum down into its constituent pieces. Then when you get to this step, I will give you the formula you need to make it from this step to this step. But then again, you'll need to use your skills to evaluate the limit. Does that answer the question? So like there is no easy summation formula for 1 over n or for 1 over I. So I wouldn't ask you to work with any of those. The only ones I'll ask you to work with directly will be the sum of 1, the sum of I, the sum of I squared, and the sum of I cubed, which are the 4 formulas we gave. Okay, I do want to change tack now just for a second and talk with you about areas and distances. So some connections to physics. This is on distances and displacement. So suppose I want to interpret the area under a velocity function v of t between two t values from t equals a to time t equals b. Right, so ooh, come on, focus, you fuck. All right, suppose I want to interpret the area under a velocity function v of t from t equals a to t equals b, meaning I want to know what that area represents. The way to do this is using something that's called dimensional analysis. We're going to draw the picture, imagine a little rectangle in there, and then see what the units of the area are. Of course, these are times, right? So let me just pretend I have some velocity function in here. Here's my t-axis. The function I'm graphing is v of t. And maybe it looks something like this. I don't know. I'll call this t equals a. I'll call this t equals b. And what I want to know is, in terms of the physics, right? In terms of like motion and what's going on in the physical world, what does this area represent? We know now that we can find the area, or at the very least, we can set up an expression for the area. We can approximate the area using rectangles, all that good stuff. But what does the area represent in the physical world? If I've got a dude moving according to this velocity function, then what does this area tell me about what the dude did? So here's the idea. Imagine we're drawing a shitload of little rectangles. So here's one of my little rectangles. Pretend it's very narrow and it's one of many, but I'm just going to draw the one. This little rectangle has a height and a width. Now, when we set up our Riemann sums, the width of the rectangle is always delta x. Here we would call it delta t. So the width of one rectangle is delta t. It's a little change in time. The height of that rectangle. So here I'm at a point, I'll just call it t. So this point on the graph would be t, comma, v of t. The height of one rectangle, this is v of t. It's a velocity. So it's a change in position. We call that like delta x over a change in time, delta t. Right? Here it's actually dx dt, right? But I'm imagining that here I've got a little interval of time. So it's a very small change in position over a small change in time. So the area of this little rectangle would be the height, v of t, times delta t, right? The width times the height, or the height times the width. And according to the discussion above, this would be like delta x over delta t times delta t. And the delta t's cancel, giving me just delta x. So the area of one rectangle is equal to a tiny change, say very small change, in position. It's the tiny change in position associated with this time interval. So each tiny little rectangle has an area that tells me the tiny little change in position over that time interval, which means the total area, which is equal to the sum of all, or you say approximately equal to, really there's two places here where I should have an approximately equal to, here and here, right? V of t is not delta x delta t, it's dx dt. And when I do this, I'm approximating. Similarly down here, the total area is not exactly the sum of the area of the rectangles, it's an approximation. But as I use more and more and more rectangles, two things happen. This becomes exact because delta t goes to 0. And this becomes exact because n goes to infinity. But for the purposes of understanding intuitively what's going on here, each little rectangle represents a very small change in position. So when you add up all the rectangles, sum of all the areas of the little rectangles, this is equal to the sum of all, each little rectangle is a small change in position. The little changes in position. So this little rectangle's area is the distance I travel over this little time interval. That's what change in position is, right? A change in position is a distance. I go from this position to this position. That's a distance. So each little rectangle represents the little distance covered by my object from the time here at the start of the rectangle to the time here at the end of the rectangle. And if you add up all of those little rectangles, you're adding up all those little distances, all those little changes in position. Change in position, remember, is a distance. So when you sum all the little distances, you get the total distance traveled. And if this argument makes you go, whoa, that's fucking cool, then you need to take physics. Because this is exactly the sort of thing that physicists do all the time, and it is really fucking cool. So the total area under the velocity curve from time t equals a to t equals b is equal to the total distance traveled. Nifty stuff, right? Anybody use the app Strava on their phone? Any cyclists here? Or use any apps like that, that tell you how far you walk or how far you drove or how far you rode your bike? The way those apps usually work isn't actually by mapping things out and then finding the distance of that path. They record your velocity using accelerometers inside the phone. The phone, you know how you can tell its orientation. The phone has very, very delicate accelerometers, which are instruments that measure forces on the phone. From those forces, it can deduce your velocity. And what it does to tell you how far you went, and there's not just your phones, but most instruments of this sort, they take your velocity curve and they find the area underneath it. That's how they figure out how far you went. And all sorts of lab instrumentation works this way too. It's very, very cool stuff. So by finding the area underneath the velocity, if you know the velocity function, then you can figure out how far you went. That's very, very cool. So you have a few problems in your homework set that ask you to do precisely this. Yeah, if you look at the ones before the sigma summation problems down here, rather than having you find the exact area and hence the exact distance, they give you a table and they ask you to use rectangles to approximate the area, and that will let you approximate the distance. And you're going to have an underestimate and an overestimate associated with whether your rectangles underestimate the area or overestimate the area. There's one small caveat here. Morning. All of this assumes the velocity function v of t is positive. If v of t is not always positive, then the area under v of t is not equal to the distance traveled. It's equal to something else called the displacement. And we'll talk about that next week when we talk about section 5.2, after I've introduced the concept of a definite integral concretely. But we're not ready for that yet. And all of the problems I'm giving you right now have these nice assumptions about the velocity function. So you don't need to worry at the moment. But I want to let you know that the velocity is equal to the area under velocity is equal to the distance traveled, as long as your velocity is always positive. Think about it like this. If I get up from my chair right now and I walk to the grocery store and walk back, then while I'm walking to the store, my velocity is positive. As I'm walking back from the store, my velocity is negative. I definitely did some traveling. The distance I traveled there is non-zero, but my displacement is zero. And if you tried to apply this technique to that velocity function, you would get zero out. And so certainly that doesn't make sense, right? If I go somewhere and come back, I have traveled a definite distance, a non-negative distance. But the area under the velocity curve would come out to zero. I'll explain why that's the case, again, in section 5.2. I feel like there was one other thing I wanted to share with you guys today. Why can't I think of this right now? Is that it? That might be it. I'm not forgetting anything. Oh yeah, one last thing before I let you go. One more tiny little thing. First, any questions on this or comments, thoughts? Okay. Overestimates and underestimates. How do I know which I'm dealing with when? Has to do with monotonicity. I've got time for this. Yeah. So when do Ln and Rn overestimate or underestimate the area under f of x? This is what I'd like to answer. And I'm going to give you a thorough answer here, but it only applies in particular situations. Suppose f of x is increasing everywhere on the interval AB. Here's A, B. So the actual area I'm trying to measure is the shaded area here. Then if I come in here, I'll draw L4 just so we have a concrete example. If I come in here with my left endpoint Riemann sum, then it will underestimate the area. Right? Because these rectangles, because the function's height, because it's an increasing function, is always lower at the left endpoint than it is on the right endpoint. That's what it means to be an increasing function. It means you're always getting bigger as we go left to right. So L4 here underestimates. And you can imagine what this picture would look like with R4. Because the function is increasing, getting bigger from left to right. If I let the height of my rectangles be determined by the value at the right endpoint, I will automatically overestimate. R4 overestimates. And this is true in general. If f of x is increasing on the interval AB, then Ln, regardless of n, will underestimate the area and Rn will overestimate the area. Similarly, if f is decreasing, the roles reverse. Now the everywhere is important. If your function goes from increasing to decreasing or from decreasing to increasing somewhere between A and B, then these rules no longer apply. But oftentimes the functions we deal with are monotone, at least on the intervals in question. So it's a useful thing to know. You can kind of imagine the picture here. Hammy boy, be good. Hamilton. No. So if I draw the picture here for R4, you can see, what do? We did L4 first up there. So let's do L4 first here. So you see that my rectangles poke out over the graph and therefore overestimate the area here. Although not by much because this function isn't decreasing too quickly. So here we end up with an overestimate because my function is decreasing and this is L4. And similarly, here the right endpoint will underestimate. So it depends on whether you're using right endpoints or left endpoints. It also depends on whether your function is increasing or decreasing. R4 here, underestimates. So if f of x is decreasing on AB, then Ln will overestimate and Rn will underestimate. There are more sophisticated ways to attack the area problem approximately using things like midpoints, trapezoids, Simpson's rule, Darboux sums, all sorts of very, very clever things exist. But what I need you guys to remember here is just these simple pictures. That if your function is monotone, either increasing or decreasing everywhere on the interval AB, then one of the sums will always be an overestimate and the other one will always be an underestimate. And the specific cases you can get by just drawing pictures and thinking about it. All right, that's all I have for you guys today. I am going to run over to my office hours because I have to get things. Oh no, we've got some time. So are there any burning questions for me before we go? I thought we were over time, but we're not. Okay, then, yeah, that really is all I have for you guys today. If you want to talk about anything else, you can come see me in office hours, use Discord, send me a Canvas message, whatever you like. Make sure you're practicing using good notation here, right? This is what matters more than anything else, is that you're effectively communicating the mathematics that you're doing. So pay attention to what your solutions look like as you write them out. Make sure that they are legible and reasonable. Drawing pictures helps a lot here. So please draw lots of pictures for those problems where you're using a finite number of rectangles, and then make sure that you're comfortable using the sigma summation notation. But that is it. I hope you guys have a lovely rest of your day. If you are taking the makeup exam because you missed exam 2, don't forget to come to office hours today. That's what will be going on there. That's it. That's all I got. So that's the end for me. Next week, Katie's going to teach us about antiderivatives, and then we're going to learn some slicker ways of finding these areas. So please knock out this homework, and then next week we'll move on to some cool stuff. Have a good weekend, guys.